Wormald, Germany 40 and German Woodward. Please pardon me for my incorrect pronunciation of your name. So whenever you are ready, you can start.
Thank you so much. Well, hello everyone. My name is Wormald with the Florida Institute of National Security. First of all, I just really appreciate the opportunity to be able to share the work with you. And just to understand more, like who's in the audience now. So my background is actually mechanical engineering. So could I get like a raise of hands in terms of like computer engineers, maybe like, first of all, wow. So like electrical engineers perhaps. Hey, there we go, yeah. Computer scientists, maybe lots of people. There we go, love it. And then other people that are like mixing right now. Okay, nice. Okay, so we got like a lot of people from computer science. And then I guess what I want to get into is specifically from the perspective of like machine learning. I think that there's a really large space that we're frankly missing in terms of trying to really deeply understand the models themselves. And I want to show you that there's a specific type here that represents one of many model types that I think can help to drastically improve our explainability while simultaneously dramatically helping the ability to run these models very quickly. So what do I mean, and then where am I coming from? So as I said, my background is actually in mechanical engineering, specifically from simulation and control and metal 3D printing. And so here's an example of a lot of the machines that we used to work with, where you can start to use lasers to melt powder, metal powder, and produce these really incredible kinds of parts. And so as with many different areas in industry, hey, let's go ahead and then use machine learning, right? As an example, maybe we can use machine learning for parameter selection, perhaps for control strategies in real time, and then ideally really help to improve the part designs. But there are actually significant challenges here that people haven't really fully realized. There's walls that hinder the honest application. First of all, these processes are very, very fast. If you're taking a laser and then you're scanning it along the path, you perhaps have it moving at a meter per second along these really tiny, like micro, like perhaps millimeter channels. And so you have to have control strategies that can help you account for those control times. Furthermore, one of the reasons that my advisors would not let me use machine learning in this field is because he didn't trust it. He did not know why and how the models were coming up with the predictions, and this is a critical insight across many different domains. But what's the trend in artificial intelligence today? So if we look at the field, and this is just a notional graph, there's a tremendous push towards increasing the model size, which by proxy significantly decreases the model explainability. My research goes in the opposite direction. I'm focusing on what I'm calling rapid XAI, where the models themselves are very explainable and very fast. And I want to remark that some models are easier to explain than others. I want to highlight this researcher. I don't think he's really gotten enough attention nowadays. He got his PhD when he was 19, and he's done a lot of fantastic research. He introduced this model architecture called DiffLogic, where every single node in the network is a logic gate. The value is that if I put this on the screen here, I'm pretty sure that everyone in this room will be able to tell me exactly what each one of these functions is doing at a low level, and then we can start to explore how to explain and understand the full model based upon this underlying architecture. And that's where I'm coming in. Because I'm making the observation that these networks are, first of all, significantly easier to explain than deep neural networks. I don't have to explain a specific floating point value and say, okay, what specific combinations of inputs are responsible for this? How does this pass through nonlinear activation functions? I know what the function means. And furthermore, logic gates can process information very quickly. I'm not going to get into the full breadth of this today, but I will show you some of the initial results. And that's where eXpLogic, this tool set, comes into play. eXpLogic can take one of these logic-based networks and then use a single algorithm to come up with a variety of explanations and add value for many people in this room. This is the algorithm. I really do not want to step through this today. That's not a good use of your time. So I encourage you to see the paper for the specific details. But what I do want to leave you with is the idea that you can understand And you could directly reproduce this entire work. It's not incredibly challenging. And this represents one of many different kinds of models that we can start to pursue as a community. So one type of explanation that we can produce is what I'm calling a function explanation. As an example, what is a specific function looking for? If I look at this output node, we can simply trace through the fan in or all the upstream functions that are connected to this. And note the reason that we can do this is because every function is only connected to 2 inputs. This starts becoming more challenging with the larger networks, but we can demonstrate real value in this case. So if we trace that fan in, we can find that, okay, those are some of the inputs that are connected to this individual class. And then notice, we'll just associate each input with a positive or negative value. Those negative values are negative because they had to pass through a NOT gate. That means that the output class is looking for a 0 rather than looking for a 1. If we repeat this across other kinds of each of the branches, you can start to add up all the inputs that are, all the different pixels that it's looking for, and then simply color the inputs according to what's important for model prediction. So we can look for what is not important for the prediction, as shown in red. We can look at what is important because it's a 1, and what's important because it's a 0. That is immediately different from what explainable approaches are using today, where you can often say, this is like what inputs are important, but it doesn't give you that nuance into how and why it's important. Note that here I'm excluding a special case for the XOR, which has a conditional dependence on whether or not it starts to produce or it's important for an input to be positive or negative, but that just changes the number of explanations that we can produce. And this is a practical realization of this algorithm. So for a model that was trained on the MNIST dataset, you can see the average of the classes on the top, and then the produced explanations in the second column. Immediately, you can start to see that, as an example for the 0, it is looking for there to be 1s on this outside location, and it's looking for there to be 0s on the inside. Furthermore, it starts to reveal some hidden trends in what the model is looking for, as an example for the 2. It does not care about this upper right-hand curve, and it's more focused on this underlying positive set of inputs that are more traditionally associated with this little curl at the bottom left. Note that we can start to expand the types of explanations by scaling each input according to how active each logic gate is, but I would encourage you to refer to the paper for more details there. However, while we can explain the importance of individual functions, we can do more. Specifically, that shows us what class 1 is looking for, but it does not tell you what caused a specific input to produce a specific output. But simply, if we look at what the model is looking for, and just simply compare it against what is present in the input, practically this is done using the not XOR, where the colors match, you can find the supporting evidence for each one of the classes that you can predict. As an example here, red represents evidence that's not important. The black represents 0s that are found that support the class. And then the yellow represents 1s that are found that support the class. And this is the binary input case. You can expand this. And this helps you to both explore and understand not only the true positives of why you're doing a good job, but also explain why you have both false positives and false negatives. And so just to explore the true positive for class 2. In the upper left-hand corner, you can see that class 2 was predicted because there are black inputs, there are 0s, in the region where the 2 is not present. It's also found that there's that looping region in the bottom left-hand corner. Similarly, you can explore why classes are not successfully predicted. If you look at the bottom left-hand image where the 2 is very flat, it was predicted as class 4. But why? If I look at the evidence for class 4, you'll notice that it found a horizontal line. And that's being used to predict class 4, because it's also looking around to say, there's not any signal above and below that horizontal line, so of course it's class 4. But now we can start to improve the model, the training data, all these things. And while that already provides some competitive advantages against traditional explanations, we can do even more. As an example, if class 1 only depends on these logic gates, we can throw away that entire top half of the model. And when you're looking at models that have many classes, that can represent a large reduction. As an example, if you run these models, well, first of all, you can throw away up to 86% of these models for the small model cases, especially when the logic gates are not entangled for different classes. And when you run these, at least on a GPU, you can reduce the inference speed by up to 10%. This does come with a small drop in model accuracy, but this does not pursue model fine-tuning, which can then further improve the accuracy of the models. Do you know that the recall has dropped significantly because of some details that I can address in the questions, if that's helpful? And there is a tremendous amount of value in real-world applications. Imagine that you're a drone that's trying to trace a specific object. You can throw, and it's been trained to perhaps follow many different kinds of objects, but now if I can focus on a specific part of the model that's really important to me right now, that helps to save resources. And now I can focus on stability, I can focus on flying. Many Internet of Things-based applications, and especially in the world of augmented reality. And so in summary, this represents a tool set to explain logic-based networks. One algorithm, many explanations. Furthermore, the result is that you can use a specific kind of model type to both not only be explainable, but to increase the inference. This is done on a GPU. I'm not even talking about the case where you can translate this to hardware. But I think more importantly here, and this is just really important to me, because this algorithm represents one of many machine learning algorithms that we might be able to find with niche and competitive advantages, not just in explainability, not just in inference speed, but targeted for your individual applications. If we as a community are creative in how we constrain these networks, you can find something which is tremendously beneficial for your use case. And I just think that just takes us being creative. That's the presentation that I have to share with you today. This is the team that I've been working with. Honestly, a fantastic team. Matthias is here today. Please talk with him as well. These are the references, and then from there, I would like to invite your questions.